Okay, welcome everyone to the week 6 live interactive session. This is NPTEL NOC24 EE-143 tutorial. Uh, the course titled Semiconductor Devices and Circuits, taught by the instructor Professor Sanjeev Sambandhan from IIC Bangalore. Uh, as usual, the schedule for my sessions is every Sunday, 5 p.m. to 7 p.m. You can reach out to me on email uh, as provided. Quickly going through the guidelines now. In case you have any query, you can either raise your hand and I'll unmute you, or you can directly ask in the chat window. Okay. And please ensure that your microphones are muted, especially when you don't intend to speak. Please take care of that. Uh, I appreciate your cooperation in making this an interactive session. So please cooperate on that. Uh, also, I'll assume that you'll have pen and paper handy along with the calculator. The session recording link and lecture notes, as usual, will be shared by the NPTEL course team in the due course of time. Okay. Now, coming to the prerequisites for this live session, the prerequisites include the following. Just a second. Yeah, the prerequisites include the Schottky contact, the small signal impedance, um, PN junctions, their electrostatics, IV characteristics, small signal impedance, and non-idealities. Okay, these were the last week's lectures that we taught, and they will be the prerequisites for this live session. And I'll assume that all of you have already attempted the assignment 6 before tuning to this session. Okay, just a second. Yeah. Okay. Now, uh, yeah. So yeah, the brief recap would include the Schottky contact, its small signal impedance as it was taught, but uh, along with that, the PN junction, electrostatics, IV characteristics, small signal impedance, non-idealities. Since nobody's here in the meeting, I'll assume nobody has any doubt on that. So we'll skip this brief recap part. Fine. And we'll directly move to the problem one, today's problem one. Fine, which is following. You need to calculate the built-in potential VBI of a silicon diode with both donor and acceptor doping concentrations of 10 to the power 15 per centimeter cube that is maintained at 300 Kelvin. Given intrinsic carrier concentration of 10 to the power 10 per centimeter cube, Boltzmann constant Kb given by 1.38 into 10 to the power minus 23 joules per Kelvin. So you need to determine what is the built-in potential of the silicon diode. Okay, please do that. Okay, I hope I was audible. I guess I had muted myself. I hope it was audible. Since there is no one in the meeting, I won't get to know if I was actually muted. Okay, it's self-explanatory anyway. If you have any doubt, you guys can ask. For now, just attempt the second question. I just realized I had muted myself. So, all right, I guess I gave sufficient time. Now I'll proceed to show the second question. Fine. Uh, let's write what we know. See, for given PN junction, right? For given PN junction, we have following. VBI, that is KT over Q, and then log of NAND by NI square, right? And yeah, let's put in the values. Your VBI would be 1.38 into 10 to the power minus 23 multiply by 300 whole divided by your Q, that is 1.6 into 10 to the power minus 19 into log of exponential of, I mean, log to the base C, your 10 to the power 17 into 10 to the power 14 whole divided by 10 to the power 20, right? If you, I mean, compute it, you'll get VBI as 0.656 volts. Now your Xn is given by 2 epsilon s epsilon naught by Q Na, your Nd times Na plus Nd, right? And your VBI raised power 1 by 2. And your xp similarly would be given by following 2 epsilon s epsilon naught whole divided by q. Then your nd whole divided by na plus nd, right? And your vbi, right? These are your formulas. If you plug in the values, you'll get uh you'll get following. You'll get xn, you'll obtain it as 2.93 micrometer. I wish there was someone in the meeting to verify these, but I don't have one right now. Okay, nevertheless. So similarly, if you compute your XP, right, your XP, it would be 2.9, wait, yeah, your XP would be 2.93 into 10 to the power minus 7 centimeters, right? And uh, wait, why would I use this? I am a better option. In fact, there is no need to use separate formula for XP, right? Once we, I mean, determine Xn, we can use following thing, right? We can write this XPNA is equal to the charge balance, right? XPNA is equal to, should use a black one instead, right? XPNA is equal to NDXN, right? And yeah, this would give XPS ND by NA times Xn. Is that fine? Now, Xn is this, XP is this. Now, what about W? W would then be Xn plus XP, right? And this would then, I mean, since 2.93 micrometer is, uh, yeah, I mean, it's much bigger than 2.93 to 10 to the power minus 7 centimeter. So depletion with W would roughly be Xn, right? This would roughly be Xn, which is your 2.93 micrometer, right? This is our W. And this was what the question asked us to compute, right? We had to calculate the depletion width for this step doping of silicon that is operated at 300 Kelvin. Okay, this is done now. What about the next question? The third one. Choose the statement that most appropriately describes the low level injection. Okay, so which of the following statements most appropriately describes this phenomenon? Okay, I gave sufficient time. So the correct option is this option A, right? That the concentration of excess minority carriers is large enough to modify the minority carriers, but it's too small to modify the majority carriers, right? We'll go with this one. So the concentration of excess minority carriers is large enough to modify the minority carriers, but it's too small to modify majority carriers, right? This is what it is, right? Okay, now the fourth question, okay? See, a PN junction has a contact potential of 0.5 volts, right? And it has a depletion width of 2 micrometer at equilibrium. Then the forward voltage at which the width reduces to 0.4 micrometer is falling. I mean, you need to provide the answer, right? So how shall we proceed for this one? Nobody joined the meeting today. Okay, somebody just joined. Fine. So how should we proceed on this one? A PN junction has, I mean, a contact potential of 0.5 volts and it has a depletion width of 2 micrometer at equilibrium. Now, when you apply the forward voltage, uh, some forward voltage, the width, the depletion width reduces to 0.4 micrometer. So you need to determine what was this forward voltage that you applied, which reduced the depletion width to 0.4 micrometer. Okay, without wasting any further time, I'll start attempting this. So our depletion width under unbiased condition when we don't apply any voltage, right? Under unbiased condition would be falling. Okay, just let me just write this right here. This would be W would be equal to 2 epsilon by Q NA plus ND whole divided by NAND, right? And your VBI minus VF, where VF is the forward voltage that you apply. And we have a square root, right? This whole thing is under a square. Now, so for constant doping concentration, let me just write, I just don't want to mess this up. For constant doping concentration, your W, right? Your W would be proportional to the square root of VBI minus VF, right? This is your W proportional to. Now, so I mean, I have two cases, right? The case one when my, there is no bias applied, let that be W1. That would be some K times square root of 0.5, right? Where this 0.5, I'm using the value of VBI, right? Rest of the things are, I mean, can be taken to be a constant. So this is K times some square root of 0.5, right? Similarly, if I mean, wait, by WT, W2, I mean the case when, I mean, some forward voltage is applied, which actually we need to compute, right? And corresponding to that, I know what is the value of the depletion width. So I'll write W2 would be equal to K times square root of your zero point 0.5 minus VF, right? And that is equal to, it is given in the question that this is 0.4 micrometer, right? This is zero point 0.4. Right. Now, if I divide these two, right? What should I divide? Just a second. I mean, W1 is also given, right? It's given that your W1 is this, right? When no bias is applied, it's 2 micrometer. So I guess I should write that as well. This is 2. Let me make this more clear. This is your W1, this is your W2. All right, this is your W2. Now, now what is W1 by W2? Your W1 by W2, that is equal to 2 whole divided by zero point 0.4. What is that? I mean, K and K would go and you'll have a square root of 0 0.5 whole divided by 0 0.5 minus VF, isn't it? Then from this, you can actually, I mean, compute what is VF, right? Your VF would be equal to 24 times zero point 0.5 whole divided by 25, right? Just verify it. And you'll get answer as VF is equal to 0.48 volts. There's only one person in the meeting. Probably that person can verify this. If indeed this VF comes about as this, right? I want you to verify that this actually gives us this value. Could you just type in chat that verified so that I get to know that yes, you indeed verified it? Just basic calculation, right? I'll just wait for, I mean, maybe 2-3 minutes for that. Please do that. Once you do that, just type verified. Okay, verified. Thank you. So now we have next question. So the question is that in this given circuit, we need to find the average voltage that appears across this 2 ohm resistor. We consider the following, right? Diode has a forward voltage drop of 0.7 volts. Parasitics are negligible, right? And the frequency of the input signal is 50 hertz, right? So please compute what should be the average voltage across the 2 ohm resistor. I'll give some 3 to 4 minutes for you all to attempt. Please do that and let me know what is the average voltage across the 2 ohm resistor. This one, right? You need to compute this V average. Guys, proceed. I'll come. Okay, I guess I gave sufficient time. Or, I mean, should I wait more? Could you just type in the chat? Should I mean, start solving myself, or should I wait? Please go ahead. Thank you. Okay, I'll start doing it now. Okay, so see, when does the diode turn on? Right? It has a forward voltage drop of 0.7 volt, right? So can I write the following? That is diode, it turns on when voltage crosses your 0.7 volt, and it turns off when the voltage goes below 0.7 volts, right? This is, I mean, uh, this is what we know, right? Now, let me draw the V input waveform. I'll use next page, okay? This is the next page, and see, this is your V in, right? And let me draw the waveform. This is your omega t. This is 2 pi. This is pi. This is TB. This is TA, right? And this is 0. Now, what about this output waveform, right? Because we are interested in that, right? So let me first. Okay, now consider that this is your omega t axis, right? This is your V out. This is your 9.3, right? Wait, now this is your 10 and this is your 9.3, right? Because there would be a drop of 0.7 volts appearing, right? That's why. So what is TA? See your TA is equals to sine inverse 0.7 by 10, right? Straightforward. It would be 0.7 by 10. And what about this TB? TB should be pi minus sine inverse. So sine inverse, okay, 0.7 by 10. Done. What about, okay, this much is done now. Now coming to the main part of the question. Okay, wait. Average value of V out. What is average value of V out? Average value of V out is uh, that would be 1 by sorry, that would be 1 by 2 pi integral TA to TB, right? Your 9.3 sine of omega t omega t, isn't it? This would be your average value of V out. Now, uh, I mean, if you, evaluate this integral, let's solve this. This would be 9.3 whole divided by 2 pi, and this would be cos of omega t, and limits would be from TB to TA, right? And this would be equal to 9.3 whole divided by 2 pi. Yeah, this would be cos of sine inverse 0.7 by 10 minus cos of sine inverse 0.7 by 10. Sorry, when putting TB, I should have, my bad. It was pi minus sine inverse, right? Because TB is pi minus sine inverse. Done. Right? This is pi. Oh, pi minus sine inverse of 0.7 by 10, right? So this is done. Now then this would be equal to 9.3 by 2 pi, right? Cos of this would be sine inverse of 0.7 by 10, right? This is equal to 2.953 volts. So what is our average voltage across the 2 ohm resistor? Therefore, average voltage across 2 ohm resistor, this is equal to 2.953 volts. Right, this is the average voltage across 2 ohm resistor, 2.953 volts. Okay, done with the fifth one. Yeah, fifth one is done. What about this one now? Please try this one. In the circuit given, you need to find the average voltage in volts across the capacitor in the time frame of t equal to 1 seconds to t equal to 2 seconds. You need to consider the following: that the capacitor is ideal, the diode has a forward voltage drop of 0.5 volts. You can neglect other parasitics and just take the frequency of the input signal as 10 hertz. Okay, please solve this. So what you need to find is that you need to find the average voltage across the capacitor. I'll wait for some time. Okay, just attempt this. Okay, so I guess I gave sufficient amount of time. This was, see, uh, it's a peak detector circuit, right? So I'll write since it is a peak detector circuit, right? Your capacitor will hold the peak value V in minus VD, right? And that is equal to 10 minus your zero point 0.5, which is nothing but 9.5 volts, right? Moving on to the next one. In the given circuit, you need to find the value of the current through the diode in milliampere at the time instant of t equal to 1.5 seconds, right? So uh, you can sorry, consider the capacitor is ideal. The diode has a forward voltage drop of 0.5 volts. Neglect the other parasitics. The frequency of the input signal is 100 hertz, right? So what should be the answer? What would be the value of the current through the diode at the time instant of t equal to 1.5 seconds? This again is trivial problem. Why? Because again, as we saw in the previous problem, this is a peak detector circuit, right? It will hold the peak value, will hold the peak value in fact, the first cycle, right? In the first cycle itself, right? Hence, no current will flow. No current will flow, right? No current would flow. It's a peak detector circuit. It will hold the peak value in the first cycle itself. That's it. So there won't be any current flow. Now let's move on to the next one, which is this question number 8, right? We are down to the last two questions now. So it's an n-doped semiconductor that is having a dopant concentration that varies as n of x equals to n0 exponential of minus ax per centimeter cube, that is used to form, a metal semiconductor Schottky contact. The junction of the metal semiconductor contact is located at x equal to 0. And this depletion region, it extends up to x equal to 2 by a, right? The semiconductor has a permittivity epsilon s, right? And given that q is the magnitude of the charge on an electron, and assuming the full depletion approximation, the magnitude of the built-in potential is best expressed as a times qn0 whole divided by a square epsilon s. So you need to find the value of this a. Okay, I'll, I guess, wait a little and then proceed it. I mean, solve it myself. Please try to find what should be the value of this a. Again, I'll wait for 5 minutes. Okay, please attempt this. All right, I guess I gave sufficient time, right? So let's go through this question 8 now. See, we are given that your n of x that is equal to n0 exponential of minus ax, right? And following thing that my xt is 2 by a. Now VBI, what is VBI? The VBI, just a second. Your VBI is equal to, it's a qn0 whole divided by a square epsilon s, right? And this is what you need to find, right? What is a, right? I guess I should write this. What is a? Let me mark this equation as suppose gamma. Okay, we'll I mean consider this equation a little later. Now d, yeah, the d by dx, right? D by dx, that should be equal to rho by epsilon naught. I mean, this is Gauss law, right? And electric field you can write as integral rho dx by epsilon naught. Straightforward, right? So what you can do is from this you get that electric field is equal to q n0 by epsilon exponential of minus ax whole divided by minus a plus c, right? And I mean then you can write that this gives you the this implies electric field is equal to minus q n0 whole divided by a epsilon. This is exponential of minus ax plus c, right? And yeah, this is one thing that we obtained. Now, once electric field is done, now we are, okay, let me add a page here. I do need a page. Okay. At x equal to 2 by a, your electric field is 0, right? So 0 would be equal to minus q n0 whole divided by a epsilon exponential of minus a into 2 by a plus c, right? C would be equal to q n0 whole divided by a epsilon and your exponential of minus 2. So we have computed C now, right? Now you'll write minus d phi by dx. That is equal to electric field, which is equal to minus qn0 whole divided by a epsilon, your exponential of minus ax minus exponential of minus 2, right? And what is your phi? Your phi would then be qn0, right? Because minus minus would go qn0 by a epsilon integral exponential of minus ax minus exponential of minus 2, right, dx. Phi of x would be equal to qn0 whole divided by a epsilon exponential of minus ax whole divided by minus a minus exponential of minus 2 times x plus c. Your VBI, your VBI would be equal to phi of 2 by a minus phi of 0. What is that equal to? Q n0 whole divided by a epsilon exponential of your minus 2 whole divided by minus a minus exponential of minus 2 2 by a, isn't it? This is your phi of 2 by a. And what about the phi of 0? That would be minus q n0 whole divided by a epsilon. When your x is 0, the second term would go, you will be left with, minus 1 by a, right? This is what you will be left with. So thus your VBI would be equal to q n0 whole divided by a epsilon. Then minus exponential of minus 2 minus 2 times exponential of minus 2 plus 1, this particular quantity, which evaluates to 0.593. Therefore, VBI is equal to 0.593 volts. Right? So this finishes our question 8. What about question 9 now? So, are you able to get it? See, you can now obtain this using this, right? See, this is your homework. Compute A from your gamma equation. Gamma is this, right? You know this, you know these quantities. The only unknown left is A. You can compute that, right? So you can compute A. I'll leave this as an exercise. Okay. So now question 9. A semiconductor has an intrinsic carrier concentration of 10 to the power 10 per centimeter cube. It has a hole mobility of 400 centimeter square per volt second. The carrier mobilities remain unaffected by doping. A PN junction diode with cross-section area of 10 to the power minus 6 uh, centimeter square is constructed with this semiconductor such that P and N side both have dopant concentrations of 10 to the power 14 per centimeter cube. It is known that the minority carrier lifetime of electrons and holes is same and it's equal to 10 to the power minus 6 seconds. The thermal voltage is exactly 25 millivolts. If a forward bias voltage of 0.5 volts is applied, uh, you need to obtain the current through the diode. Okay. I'll wait. Please attempt this one. I'll wait for 5 minutes. Okay, so I gave enough time. Now I'll proceed to solve this question. Okay, your Ni is 10 to the power 10 per centimeter cube. Your area of cross section A is 10 to the power minus 6 centimeters square. Hmm. What about hole and electron mobility? Your hole mobility, that is 400 centimeter square per volt second. Your electron, sorry, your electron mobility is 1000 centimeter square per volt second. Your Na is equal to Nd is equal to 10 to the power 14 per centimeter cube, right? Your tau n is your tau e, and that is 10 to the power minus 6 seconds. This is something that is already given. And your Vt, which is Kt by Q, that is, 25 millivolts. Your Va, is it Va? Yeah, the forward bias voltage, right? That forward bias voltage Va is 0.5 volts. What you need to find is J. What is this J? So let's take a fresh page and proceed to solve it. You know that J is Js exponential of QVA by KT and so on, right? This is something that we know. So if you put in the values, this would be Js times exponential of, this would be, VA is 0.5 and this KT over Q is 25 into 10 to the power minus 3. So I can write that in the denominator and then minus 1. So what is J? Js times 4.85 into 10 to the power 10. Js is 4.85 into 10 to the power 8. What about, sorry, J is Js times this expression. What about Js? See, your Js is this. Js is given by your Ni square root of your KTQ. Then you have this mu p by tau p raised power 1 by 2, 1 by nd plus mu n by tau n 1 by 2, 1 by na, right? Then your Js is equal to 130.50 into 10 to the power minus 11 ampere per centimeter square. This implies your J is equal to 0.631 ampere per centimeter square. Your I is J times A, right? So therefore, your I would be equal to 0.631 into 10 raised power minus 6 amperes. Okay, so that gives us the I. So yeah, that was what I needed to compute, right? Because in this question we were asked to find the I, the current through the diode. So this would be 0.631 microamperes. So if there are no more doubts, I mean, I'll be finishing this session right away. Any doubts? Okay, I'll take that as a no. Okay, no doubts. Thank you. Fine. So I guess we should end the meeting here. Okay. Thanks for tuning in. Thank you. You're welcome. Okay. Bye.